Hello, I present my research whose title is Application of Solution Blow Spinning Technique for Non-Woven Fiber Production Using PVA. The authors of this work were Paulo Sérgio Moreira and Professor Michele Sostag Meruvi, Pontifícia Universidade Católica do Paraná, Department of Mechanical Engineering. Introduction. The most common treatment for those who have had any type of injury is organ or skin transplantation. The major problem with this method is that the body does not always accept the transplant, and there are few donors, causing long waiting lines for an organ or tissue. So to solve this problem, we have the hydrogels to help us. Their properties are similar to the body tissues more than any other synthetic biomaterial. PVA is one of the most produced synthetic resins in the world. It's a semi-crystalline polymer with important characteristics like non-toxicity and biocompatibility. The most used method to produce nanofibers from hydrogels is electrospinning. However, it's a very expensive method due to the energy source. As a simple and cheaper method, however, stands the solution blow spinning, a technique developed by Medeiros that uses concepts of electrospinning and conventional rearing. The figure 1 shows a basic SBS scheme. The solution is pumped into a pressurized gas stream directed to a polymer to the collector. So the elements used are simple: pressurized gas, injection pump, pressure gauge, nozzle, and collector. The aim of this work is to produce an equipment and determine process parameters that allow to reliable production of PVA fibers intended to use as drug carrier in a human tissues injury treatment. Experimental method, preparation of solution. For the PVA water solution preparation, you used a PVA neon with hydrolysis degree of 18% was added to water at the 6th degree until a concentration of 100 gl for total mixing. The composition was kept for 2 hours in agitation in a Britannia blender and another 24 hours at rest. To allow the bubbles formed during the mixing to finish, that step is accompanied of a color change from witching to transparent and decreasing in viscosity. A second solution was prepared by adding 20% of 70% ethyl alcohol to water, that is 18 ml of water and 200 ml of alcohol were used to achieve a PVA concentration solution of 100 gl. Experimental method. First experimental setup. The setup is a PLA printed model, modeled using the CAD software CATIA V5. In figure 2, the CAD model parts are numbered from 1 to 7. The idea for this prototype was to develop pieces that were easy to fix together, like a Lego. All parts except the step motors are fitted together without the use of screw. So in figure 2, you can see the parts. The part 1 is stepper support, part 2 plunger, part 3 M10 spindle, part 4 base, part 5 sitting support, part 6 lower nozzle, part 7 top nozzle. So our experimental setup is more or less like the figure 1. It's and use a rotation and the collector of 75 RPM, a 3 ml syringe, and a 5 volts hose stepper motor, and an Arduino to control this motor. The syringe nozzle is inserted directly in the compressor R tube, this tube head. To avoid possible air recirculation, the nozzle are remodeled to facilitate the passage of air. So the air comes here, the solution comes here, and here the air and the solution comes out. As seen in previous works, to produce PVA fibers, it's necessary to use a heat source. For this work, a hot air blower was used with a temperature of 3 degree and 300 degree and 1500 degree. For the experimental method, the second experimental setup, the other components are the same as the previous experimental. The difference, we changed the stepper motor for the NEMA 70 and the compressor. So during the tests of the previous apparatus, it was observed that the stepper motor used did not have enough torque to keep a constant injection rate. Because of this, the stepper motor was replaced with a NEMA 27. Results. First experimental setup. For this experimental setup, for the alcohol solution with and without alcohol was used to verify influences for the drying and fiber formation, and the temperature of heat blower was also changed. So in figure 6, showed the optical microscope images of PVA samples prepared from the A, polymeric water solution, and B, polymeric alcohol mixed solution with both with air blower at temperature of 300 degrees. So in figure A, the optical microscopy image shows the morphology of the sample prepared from the PVA aqueous solutions. The samples have an apparent irregularity on their fiber surface when compared to the fibers of the samples in the figure B, which were prepared from the PVA alcohol mixed solution and were more uniform. The non-uniformity of surface may have been induced by the drawing of fiber, since the alcohol evaporates more easily and to dry sample is a shorter time. So in the figure 7 shows the optical microscopy images of PVA samples prepared from the E, polymeric water solutions, and B, polymeric alcohol mixed solution, both if air blower at the temperature of 550 degrees. So it's possible to observe the fibers more transparent than the 300 samples. So in the samples shows in figure 6A, it's not possible to see very clearly the fibers. But in samples prepared with the solution to which alcohol was added, figure 6B, it was possible to see fibers forming a web. So in the figure 8 shows the X-ray diffraction spectra from samples prepared from alcohol at the solution at 300 with alcohol and 150 without with alcohol, and from alcohol solutions at 300 degrees without alcohol, and 550 degrees without alcohol. So we can see there's no there's no any kind of alteration with the addition of alcohol in solution or use the high temperature. So the results of the second experimental setup, in all the tests, the solutions contain the concentration of alcohol, and the only difference to the previous tests was that for some tests, with this method, the solution was heated before application to see if there are visible difference in fiber formation. So in figure 9, shows the optical microscopy images of PVA samples prepared from the heated polymeric alcohol mixed solution with air blown at the temperature 550 degrees. So the figure 10 shows the optical microscopy images of PVA samples prepared from the polymeric alcohol mixed solution with air blown at temperature of 550 degrees. So the conclusions. All the samples showed some type of defect in the formation fibers. However, using the second method, where the injection control is done by the NEMAS 17 stepper motor, there was an improvement in tissue uniformity. With this, it's possible to obtain fibers with better quality if the necessary optimal parameters for sample injection speed are determined. The use of alcohol in solution improved the surface quality of the fibers, probably due to the ancient drying, and this use not affected the crystallinity of samples as verified from the diffraction spectra. As for the temperature, more tests are necessary to understand the transparency of the samples prepared at a temperature of 550 degrees. Although the difficulties in obtaining PVA fabric using the SBS method in the first tests by adjusting the parameters, it may be possible to achieve conditions that may improve fiber formation and reduce the agglutination in the samples. And this is it. With that, I conclude my presentation. Thanks for the opportunity.